Hello everyone. Today we will talk about the urban water network and pressure management. This course focuses on urban water distribution networks and the role of pressure management within these systems. Urban water networks are critical infrastructures that ensure the reliable delivery of water to residential, commercial, and industrial users. Understanding how these networks function is essential for effective operation and management. Pressure management plays a central role in water distribution systems. Pressure levels directly affect service quality, system reliability, and the occurrence of water losses. Inadequate pressure can lead to service interruptions, while excessive pressure increases leakage rates and accelerates infrastructure deterioration. By the end of this course, learners will understand the basic structure of urban water networks and the fundamental concepts of pressure and pressure management. This knowledge will provide a foundation for more advanced topics, including data-driven leakage detection and district-metered area analysis covered in the following courses. Urban water distribution systems are designed to deliver potable water from supply sources to end users in a safe, reliable, and continuous manner. These systems form the backbone of urban water services and must operate efficiently to meet daily demand. A typical distribution system consists of transmission and distribution pipelines, storage facilities, and various control elements. Together, these components ensure that water is transported, stored, and delivered under appropriate pressure and quality conditions. In urban contexts, water distribution networks operate at a large scale and serve dense populations. High demand variability, complex network layouts, and the need for uninterrupted service make urban water distribution systems particularly challenging to manage. Understanding this context is essential for effective pressure management and network operation. Urban water networks are composed of several key components that work together to deliver water efficiently and reliably. Pipes form the physical structure of the network, transporting water from supply sources to end users. Junctions connect different pipe segments and allow water to flow through multiple paths within the system. Valves and pumps are critical control elements within the network. Valves are used to regulate flow, isolate sections for maintenance, and manage pressure conditions. Pumps are used to overcome elevation differences and boost pressure where gravity alone is insufficient to meet demand. Reservoirs and storage tanks play an important role in balancing water supply and demand. They help stabilize pressure within the network, provide storage during peak demand periods, and ensure water availability during emergencies or maintenance activities. The topology of a water distribution network refers to how its components are connected and how water flows through the system. Two common types of network topology are branched networks and looped networks. Branched networks have single flow paths, while looped networks provide multiple alternative paths for water flow. Network topology directly affects redundancy and resilience. Looped networks generally offer higher reliability because water can be rerouted if a pipe fails or maintenance is required. Branched networks, while simpler and less costly, are more vulnerable to service disruptions. Network structure also has important implications for pressure behavior. The number of flow paths and their configuration influence how pressure is distributed across the network. Understanding network topology is therefore essential for effective pressure management and system design. Geographic information systems play a central role in the management of urban water networks by providing a spatial representation of infrastructure assets. This enables pipes, valves, pumps, reservoirs, and other components to be mapped accurately and viewed as a connected system rather than isolated elements. In addition to visualization, this supports asset inventory and data integration. Infrastructure attributes such as pipe diameter, material, installation year, and condition can be stored and linked directly to spatial features. This centralized data structure improves data consistency and accessibility across operational teams. This also supports analysis and decision-making in water network management. By combining spatial data with operational information, GIS-based systems help identify critical assets, define pressure zones, and support leakage detection and maintenance planning. This analytical capability makes GIS an essential tool for effective pressure management and network operation. Pressure in water networks refers to the force exerted by water on the walls of pipes and system components. This force is essential for transporting water through the network and ensuring that it reaches end users at an adequate level. Two main types of pressure are considered in water distribution systems. Static pressure occurs when there is no water movement, such as during periods of zero demand. Dynamic pressure, on the other hand, occurs when water is flowing through the network and is influenced by demand, friction losses, and network configuration. Pressure is commonly measured using units such as bar or meters of water column. Pressure sensors and gauges are installed at key points in the network to monitor pressure conditions. Understanding how pressure is defined and measured is a fundamental step toward effective pressure management in urban water networks. Pressure behavior in urban water networks is influenced by several interacting factors. One of the most important factors is elevation. Areas located at higher elevations require higher pressure to ensure that water can reach end users, while lower areas may experience excess pressure if not properly managed. Demand variation is another key factor affecting pressure. As water consumption increases during peak hours, pressure levels may drop due to higher flow rates and friction losses in the network. Conversely, during low demand periods, pressure levels may rise. Pressure also changes over time. Daily demand cycles, such as higher usage in the morning and evening, and seasonal variations, such as increased consumption during summer months, cause temporal fluctuations in pressure. Understanding these behaviors is essential for designing effective pressure management strategies. Pressure zones are defined areas within a water distribution network that are operated under similar pressure conditions. The main purpose of pressure zoning is to control and stabilize pressure across different parts of the network, especially in urban areas with varying elevation and demand characteristics. Pressure zones are typically created based on elevation differences, demand patterns, and the overall structure of the network. By separating high and low elevation areas into different zones, utilities can avoid excessive pressure in lower areas while ensuring adequate pressure in higher zones. From an operational perspective, pressure zoning provides several benefits. It enables more precise pressure control, reduces the risk of overpressure-related leaks and pipe failures, and improves the overall reliability and efficiency of the water distribution system. Pressure control elements are used to regulate and maintain appropriate pressure levels within urban water networks. One of the most common control devices is the pressure reducing valve, or PRV. PRVs are installed to reduce excess pressure and keep pressure within predefined limits, protecting infrastructure and reducing leakage. Pumps and booster stations are used in areas where pressure is insufficient, such as high elevation zones or distant parts of the network. These elements increase pressure to ensure that water reaches all users with adequate service levels. Different control strategies can be applied depending on operational needs. Fixed pressure control maintains a constant pressure level, while time-based or demand-based control adjusts pressure according to consumption patterns. Selecting the appropriate control elements and strategies is essential for effective pressure management. Pressure management refers to the systematic control of pressure levels within a water distribution network. The primary goal of pressure management is to prevent excessive pressure during low demand periods while ensuring sufficient pressure during times of high consumption. Overpressure is a major concern because it increases leakage rates and accelerates pipe deterioration and failures. Underpressure, on the other hand, can lead to poor service quality, customer complaints, and in some cases, health risks due to potential contamination. Effective pressure management aims to balance these risks by maintaining pressure within acceptable operational limits. By doing so, utilities can protect infrastructure, reduce water losses, and ensure a reliable and continuous water supply for end users. Pressure has a direct and well-established relationship with leakage in water distribution networks. As pressure increases, the rate at which water escapes through existing leaks also increases. Even small increases in pressure can lead to disproportionately higher leakage volumes. Excessive pressure places additional structural stress on pipes, joints, and fittings. Over time, this stress weakens infrastructure components and increases the likelihood of pipe bursts and failures. These failures not only cause water losses but also disrupt service and increase operational costs. In the long term, unmanaged pressure accelerates network degradation. Asset lifespan is reduced, and the frequency of maintenance and repair activities increases. Understanding the relationship between pressure and leakage is therefore critical for developing effective pressure management and loss reduction strategies. Water loss in distribution networks refers to the difference between the volume of water supplied to the network and the volume that is billed to customers. These losses are generally classified into two main categories: physical losses and apparent losses. Physical losses occur due to leaks, bursts, and overflows in pipes, joints, and fittings. Apparent losses, on the other hand, result from issues such as inaccurate metering, data handling errors, or unauthorized consumption. Both types of losses reduce the efficiency of water distribution systems. Several factors contribute to water loss, including aging infrastructure, excessive pressure, and insufficient maintenance practices. From an operational perspective, high water loss leads to increased non-revenue water, higher energy consumption, and greater operational costs. Addressing water loss is therefore a key objective of effective pressure management strategies. Pressure management is widely recognized as an effective strategy for reducing water losses in distribution networks. Unlike reactive approaches that focus on repairing leaks after they occur, pressure management emphasizes preventive control to minimize the conditions that cause leaks in the first place. By optimizing pressure and maintaining it at the minimum level required to provide adequate service, utilities can significantly reduce stress on pipes, joints, and fittings. This proactive approach helps prevent the formation of new leaks and slows the progression of existing ones. The benefits of pressure management include lower leakage rates, extended asset lifespan, and reduced maintenance and repair costs. As a result, pressure management serves as a cost-effective and sustainable strategy for improving overall network performance. A district metered area, or DMA, is a hydraulically isolated section of a water distribution network where inflows and outflows can be accurately measured. By defining clear boundaries, utilities can monitor water movement within a specific area of the network. DMAs are created to improve the monitoring and control of water losses. By isolating smaller sections of the network, utilities can detect abnormal flow patterns more easily and identify areas with high leakage or operational issues. This targeted approach is far more effective than analyzing the entire network as a single system. DMAs are closely linked to pressure management. Localized pressure control within a DMA allows utilities to adjust pressure levels according to local conditions, reducing leakage and improving network performance. DMAs therefore provide a practical framework for implementing effective pressure management strategies. The structure of a district metered area is based on clearly defined hydraulic boundaries. These boundaries are created using valves and other control devices to isolate the DMA from the rest of the network. Proper boundary definition is essential to ensure accurate monitoring and analysis. Within a DMA, flow meters are installed at inlet points to measure the volume of water entering the area. In some cases, outlet measurements are also used to improve accuracy. These measurements provide the data needed to assess water balance within the DMA. The operational logic of a DMA involves comparing measured inflow with expected consumption based on customer demand. Significant differences between these values can indicate abnormal flow patterns, such as leaks or unauthorized usage. This approach allows utilities to detect issues early and respond more effectively. Monitoring pressure within district metered areas is a key component of effective network management. Pressure sensors are installed at critical points within the DMA to collect pressure data either continuously or at regular intervals. These measurements provide insight into how pressure behaves across the network. Temporal monitoring allows utilities to analyze pressure variations throughout the day and night. For example, unusually high pressure during low demand periods or unexpected pressure drops during normal operation can indicate potential problems such as leaks or malfunctioning control devices. From an operational perspective, pressure monitoring supports early detection of leakage risks and infrastructure stress. By identifying abnormal pressure patterns, utilities can take timely corrective actions and optimize pressure levels, improving both network performance and asset protection. Pressure management in urban water networks faces several operational challenges. One major challenge is aging infrastructure. Older pipes and components are more vulnerable to pressure fluctuations and are more likely to fail under excessive or poorly controlled pressure conditions. Data availability and data quality also pose significant challenges. Incomplete network records, outdated asset information, or limited sensor coverage can reduce the effectiveness of pressure monitoring and analysis. Reliable pressure management depends on accurate and timely data from across the network. Organizational coordination is another important challenge. Effective pressure management requires close collaboration between operational teams, maintenance crews, and planning departments. Aligning short-term operational actions with long-term infrastructure strategies is essential for sustainable pressure management. In practice, pressure management involves daily operational decisions based on network conditions and demand patterns. Operators may adjust pressure settings to respond to changes in consumption, seasonal variations, or abnormal pressure readings detected by monitoring systems. Pressure management is closely integrated with maintenance activities. Pressure data can be used to prioritize repairs, identify vulnerable network sections, and coordinate field interventions more effectively. This integration helps prevent failures and reduces the impact of leaks on service delivery. GIS-based systems play an important role in practical pressure management. By visualizing pressure zones, assets, and monitoring data, GIS supports informed decision-making and improves coordination between operational teams. This spatial perspective enhances the effectiveness of pressure management strategies. This course highlighted the importance of understanding urban water network structure and pressure behavior. Network topology, components, and spatial characteristics all influence how pressure is distributed and how the system responds to demand and operational changes. Pressure management plays a central role in ensuring service quality while minimizing water losses and infrastructure stress. By maintaining pressure within appropriate limits, utilities can reduce leakage, extend asset lifespan, and improve overall network performance. The concepts introduced in this course provide a foundation for more advanced analysis. Understanding pressure behavior and management is essential for data-driven leakage detection and DMA-based approaches, which are covered in the next course. This course focused on the fundamentals of urban water networks and pressure management. These concepts form the basis for understanding how water losses occur and how they can be controlled through operational strategies. In the next course, the focus shifts from pressure control to data-driven analysis. Learners will explore how data from sensors, meters, and GIS-based systems can be used to detect leakage, analyze patterns, and support targeted intervention planning. This progression from foundational concepts to analytical methods reflects the practical workflow used in modern water utilities. By building on the knowledge from Course 421, learners will be prepared to engage with data-driven leakage detection and decision support techniques in Course 422.